As we continue to talk about work and energy, today we introduce the concepts of power and efficiency. So to start out with, let's define power. The simple definition is just that power is work per time. So mathematically, we can say then that power is the time derivative of work, and it's a scalar quantity just like work. But earlier we defined work by the scalar product of force and the change in position. And then we integrated that over the entire path to come up with the total work. But if we take that definition and apply it to the earlier definition of power, we can say that power is the scalar product of force and the derivative of position with respect to time. And that last vector, the derivative of position with respect to time, is the velocity. So, in words, we can say that power is the force times the velocity in the direction of the motion. So the units of power, well, the units of work were force length, for example, foot-pounds or Newton meters. And so power will just have units of force times length over time. So in the U.S., that would the units we typically work with are foot-pounds and seconds. But often we express power in the U.S. system in horsepower. And 1 horsepower is equal to 550 foot-pounds per second. In the SI system, work is Newton meter, so power would be Newton meter per second. Remember, a Newton meter we also call a joule, and a joule per second we call a watt. And to convert between the two systems, 1 horsepower is equal to 746 watts. Because often, for example, in an electric motor, we might define its output in horsepower, but the electrical power coming in we might define in watts. So we have to convert between the two of them occasionally. So here's a simple example. If we want to lift this 200 kilogram crate at a speed of 2 meters per second, how much power is required? And I should say here we'll do this at a constant speed of 2 meters per second. Because if the speed is constant, then we know that the tension in the cable is equal to the weight of the crate, because there's no acceleration of the crate. So we will say that the motor is pulling with a tensile force equal to the weight, which in this case works out to be 1962 newtons. And so that's the force. We multiply that by the speed of 2 meters per second, and we come up with 3,924 Newton meters per second, or 1924 watts. And since we should use proper SI prefixes, we'll make that 3.92 kilowatts. So that's a simple example of calculating the power. Now in this problem, that power that we calculated, the power to lift the crate, would be the output power of the motor. Now the power that we have to input to the motor is always going to be greater than the output power. So in this case, say we have an electric motor, this is saying we have to provide more electric power to the motor than what we're going to get out and to do the work. So we introduce the term efficiency, which is simply the power out divided by the power in. And it's important to note that all machines will have efficiencies less than 1, because there's always energy loss due to friction, heat, etc. So back to the example problem that we just worked. We'll say now that the motor is operating at 70% efficiency. And in your electrical courses you might learn a little bit about motors and efficiency, and the efficiency is not a constant. It depends on what load the motor is operating at, but we'll say in this case again 70% efficiency. So we already calculated the output power of the motor as being 3.92 kilowatts. And so now just using that definition of efficiency, which we said is 70% or 0.7 as P out over P in, then we can say that the output power divided by the efficiency of 0.7 gives us the input power. So in this case we have to supply the motor with 5.61 kilowatts to be able to have the working power, the output power of 3.92 kilowatts. So in the next class we're going to keep going with work and energy, but now we'll introduce the principle of conservation. of energy. So when we talk about mechanical energy, we're talking kinetic and potential energy. And when we don't have forces such as friction, which we call non-conservative forces, in particular when we have weights and springs that are conservative forces, then we can look at work and energy in the form of saying that energy is conserved. So the total of kinetic and potential energy from one state to the other will be the same.